Okay, let's start. So I have to say, like many scientists, I am a quite curious person. So, but the point is that my curiosity gets to the highest level when I deal with diffraction experiments in which I can see phase changes, changes in intensities, changes in peaks position, and so on and so forth. So my group, of course, because of this, works a lot with crystallographic experiments, and we are mostly expert on ab initio structure solution determination from powder X-ray diffraction data. And this means that we also work on a laboratory scale instrumentation, not only synchrotron-based experiments, and we like to deal with non-ambient crystallography, which means measuring in situ our materials under an external stimuli and see what's happened if there are phase changes or how are the host-gas interaction and so on. So you can imagine that metal organic framework are the best platform for this kind of experiments. Of course, they are crystalline, and now we also know they can be amorphous, they can transform into crystalline, they can be disordered, and so on and so forth. And that's why my group really focused on these experiments. And now we are also combining more complex experiments. So we are combining X-ray diffraction with X-ray absorption spectroscopy to go deeper in the characterization of such systems. Okay, so let me just give you an overview on the motivation behind the interest in performing in situ X-ray diffraction on metal organic frameworks. Of course, this means that we are monitoring a diffraction data under a physical parameter change during the monitoring of the diffraction angle and intensities. So this means that if we can apply an external stimuli that is, for example, temperature variation, of course, but also variable pressure, variable gas pressure, or variable vapor pressure loading, we can locate the gas binding site inside the MOF pores. So we can get to a good and deep understanding of the adsorption behavior and reactivity of these materials. Of course, if you are dealing with flexible MOF, then you can also determine structure variation during these experiments. And I would like to point out also that for laboratory scale, it's possible, and we have seen the presentation of my chair yesterday, it's possible to develop special conditioning chambers for the use of in situ X-ray diffraction in the laboratory. So this is quite interesting because people normally think that this experiment can be only done at the synchrotron beamlines. However, some of the most common problems can be solved also at the laboratory scale. It doesn't need always to have such high resolution or the fancy instrumentation we have at the beamlines. However, of course, conventional instrumentation cannot tackle the sophisticated problems that we can solve by going to the synchrotron. So we don't have in-house neutron sources at our laboratories. Of course, we don't have such high resolution, which in some cases is interesting, is necessary for some experiments. So I have chosen 3 examples. The 3 of them are quite recent and still in progress. And the first one deals exactly with laboratory scale conditioning chambers we have in our laboratory that we have used to determine the key properties of a material that have shown to be able to capture CO2 even in the presence of water. So this means that in this case, you will see a simple experiment performed in the laboratory that has given us the key information for solving this experimental problem. So the MOFs, the selected MOFs is a well-known paddle wheel MOF already published back in 2007 by Prof. Bang-Lin Chen. Is a paddle wheel based metal organic framework and the pillar layered one in which there is also an entanglement of two nets. And the CO2 absorption of these metal organic frameworks, properties of these metal organic frameworks shows a stepped behavior of the adsorption isotherm. And so we were asking ourselves in collaboration with Jorge Navarro, who was the expert performing the adsorption experiments, why there is this stepped behavior in the adsorption isotherm. So we try to deal with this question with laboratory scale instrumentation. We have a very simple system. Is a goniometer head that can be mounted both on single crystal and on powder X-ray diffraction instrumentation with a capillary that is invisible in this slide, but is there, believe me. And we can activate in situ the sample. We can load the gas pressure up to 50 bar. And we can measure our diffraction on, in this case, on a single crystal. So we growed the single crystal of this MOF. We solved the structure of the synthesized phase. And we have seen that in this phase, there is a, we use this one, there is a water molecule that is inside the channels. And this is actually the solvent in which the MOF is produced. So after activation, there is a small volume change, but and only the rotation of the pillars of this MOF, which are disordered over 3 positions. So simple in situ experiment in which we just activated the sample. Then we performed the CO2 loading, and we observed that the CO2 molecules goes exactly in the same position of the water molecule. If you superimpose the two structures, you can see that this in this picture on the right, you can see that the oxygen, one of the oxygens of the CO2 molecules goes exactly in the position of the water molecules, which means to me that this is the primary binding site of this system. So for the sake of time, I can't show all the adsorption experiment that Jorge Navarro has performed, but believe me, the breakthrough curves shows that CO2 can be absorbed also when there is a wet flue gas running through the column, and we are still not understanding why there is this stepped behavior in the CO2 adsorption process, because we just see a CO2 molecule loading into one adsorption site of this MOF with not too many changes. But then, so giving a close look to this system, we discovered that the 6% of the volume was still empty in the synthesized form, which means that maybe these voids are accessible and are maybe accessible to another gas different from water. So we performed another experiment in situ with our laboratory scale conditioning chamber, and we obtained this crystal structure in which you can see that the CO2 molecules interact with the water molecule and goes exactly in those voids of the structure. So there is in some way a unique pocket that is available for CO2 when water is around and permits this dynamic behavior of the system. So this is just a summarizing slide to show you that you can perform CO2 loading, activation, and then again, CO2. Continuing with diffraction experiment, the second example deals with high resolution X-ray diffraction. So in this time, I would like to show you how much is the power of high resolution when needed on a metal organic frameworks when you perform in situ experiments. This was done by Stephanie Terruzzi and Rebecca Wismara, and Stephanie has a presentation just after mine, so I will try to do not spoil her too much her work. She will get into details of this system. But so actually this is an iron-3 based, pyrazolate based MOF that was published by the Jeff Long group in 2013. This MOF is highly stable, has a very high stability, and this was also determined by Professor Miller in 2021 in this nice paper, and we performed a thermodiffraction experiment with another laboratory scale, very simple laboratory scale conditioning chambers. The CO2 properties are very interesting, recyclability is high, and Stephanie will show you the details. And so we decided to see to look at the details of this adsorption process through X-ray diffraction experiments. So in this case, the system is rigid, is highly stable. So changes in the diffraction will means only changes in the intensities. And high resolution is quite good for this kind of experiment. So we performed the experiment at ID22 at the SRF, where they have a gas loading system. And then we applied all our, let's say, computational tools for the structure solution and refinements on the CO2 loaded X-ray diffraction data. This means that we were able to describe the unit cell variations and then locate the adsorption sites of the CO2 molecule, which are 3, and we have seen that side-on interaction are preferred over ends-on one, and also to describe that the disorder of the benzene rings diminishes by raising the pressure. Okay. But what is more interesting of this work is that from the determination of the occupancy of the CO2 molecules, we were able to build the CO2 adsorption powder X-ray diffraction adsorption isotherm, as we call them. And by applying the Langmuir model, we were able to model the isotherms, which means that from the modeled isotherms, you can also calculate the heat of adsorption of this process. So as a comparison to show you that how big is the power of X-ray powder diffraction when a good data treatment is performed, I can show you the comparison between volumetric adsorption isotherms and the respective QST, so heat of adsorption in blue, and the same determined by powder X-ray diffraction with the relative heat of adsorption determined by applying the Clausius-Clapeyron equation from the modeled isotherms. And so this is another example of how much detailed the information can be if a good data treatment can be done on powder X-ray diffraction data. So I move to the last topic of my talk, and I need some water. So that's okay. Thank you. So Professor Carlo Lamberti, many of you already, maybe many of you know him. He was professor at the University of Turin. In 2018, he has this vision of writing a very good project and putting together 5 different Italian institutions with the aim of, thank you. Okay, sorry. With the aim of developing a new X-ray absorption technique at the HE-Elettra Synchrotron in Trieste. So he then suddenly passed away in 2019, unfortunately, but the group has worked a lot on this project, and we are still working on it. So I would like to show you some of the results we have obtained in the development of this new technique, and show you that this is the reason why we are moving also to absorption, X-ray absorption experiments. So the project deals with the development of an ambient pressure soft X-ray absorption spectroscopy chamber. And this will be explained in detail at the end of this session by this guy is there, Luca Braglia, who is also here, mounting the cell on the beamline. And so this technique, normally electronic properties of metal organic frameworks are determined by hard X-ray experiment at the synchrotron. And almost all experimental conditions can be reached with hard X-rays. You can imagine any type of experiment, and now they can perform it for you. At the synchrotron, but so in the soft X-ray regime, the information information you can get from this technique are quite interesting, because they directly probe the core level transition to unoccupied states, and this means that you can measure the transition of the D-many manifold transition metals, but also you can follow the K-edge of the lighter elements, which means monitoring the K-edge of oxygen, nitrogen, and so on. This ideally, the technique is now getting better and better. So you can imagine that you can measure gas loading on a MOF and monitor the oxygen K-edge of a gas probe molecule and the metal site in the MOF. And so Luca is expert of this technique, and he will show you some work. And this is the group. Oh, it's going on. Okay, alone. So we have performed several experiments in the last 1.5 years. And I will show you only the one related to the direct observation of Langmuir and cooperative adsorption of CO through a spin transition mechanism on iron-2-based MOF. Luca has the talk in this session, and we will explain you the story behind these Journal of Physical Chemistry letters, in which we were able to understand few defective sites on HCAS1 surface. Then we are dealing with more complex experiments, such as determination of structure of water in water harvesting MOFs, or catalytic experiments, such as following the reaction step of methane to methanol oxidation on the MILA-100 iron, or characterization of elusive active species during catalytic experiment on biomimetic MOFs. Marco Vandone is my PhD student. He has a poster, and he is very good in explaining these experiments. So you can understand that the motivation behind the use of this technique in combination with X-ray diffraction experiment stay in the fact that with this technique we can understand the electronic properties at the local level in metal organic frameworks. So by coupling the diffraction, where you can have a picture of the average structure, and X-ray absorption spectroscopy, it's kind of a good tool if you want to describe in detail host-gas interaction during adsorption processes, catalytic experiment, molecular sensing, and so on. Another tool that we are going to use in the next months is the combination of adsorption spectroscopy, variable pressure, X-ray powder diffraction, and PDF analysis on the diffraction data, just to improve again the detail of information we can get. So let me move to the last experiment. So we started with a very difficult system to test the cell at the upper beamline at the HE-Elettra Synchrotron on metal organic frameworks. We were crazy in choosing this system because they are very sensitive one, so it's quite kind of difficult to deal with sensitive materials, but the results are quite encouraging. So the two systems were selected because they were provided by Jeff Long Group. They were published by the group in 2016 and 2017, and they were selected because they have in common the fact that both possesses okay, animation goes. They both possesses open iron 2 metal sites. We are capable of pieback donation, so which means that they can selectively separate carbon monoxide from other gases that, you know, carbon monoxide possesses low line pi star orbitals. However, these two systems react in different ways. So in one case, for iron Bt tri, the behavior is just a Langmuir type behavior in which the iron 2 sites works as isolated sites, and the CO adsorption proceeds with a high spin to low spin transition on the single metal sites. On the contrary, iron 2 BTDD is a different system because the coordinatively unsaturated metal sites in this system are closely linked into the channels, and the electronic properties of these materials change in a concerted way while the CO binds the iron 2 sites. So this behaves not only as a selective adsorbent, but also as a cooperative one, mimicking the biological systems that have a cooperative behavior during adsorption of these kind of molecules. So we were interested in trying to understand if with soft X-ray adsorption spectroscopy, we were able to discriminate between these two systems and to understand the electronic properties of these MOF during the experiment. So this was performed by Luca and Marco and me. I was there. We started with iron Bt tri, the Langmuir type adsorption system. And I will go quickly, but you can observe that while sending even a small amount of CO into the gas flux running into the conditioning chamber, it's possible to see a sudden increase of the L3 edge solder, which is indicative of the high spin to low spin transition of this iron 2 metal center. The same does not occur with other gases, and this behavior is very reversible, which means that if you take off the CO from the gas flux, the high spin iron 2 metal size recovers in few seconds, so immediately. This is different for iron BTDD because the cooperative behavior, the stepped shape adsorption of CO means that the high spin to low spin crossover can occur only after a certain partial pressure of CO. And this can be seen from this graph, in which you can see that the same change observed for iron Bt tri is observed here only after 0.2 partial pressure of CO. And this spin transition is stable if you take off the CO from the gas flux, which means that the system needs some energy to recover from the spin crossover, and we needed to reactivate the sample at 95 degrees to go back to the original state. So we are now in the hands of theoretical chemists that we will go deeper in the characterization of the electronic properties of this system. But at first, I'm just showing to you the first calculation done with crispy-4-Sachs that show a very good agreement between the experimental high spin to low spin iron 2 on iron BTDD and the theoretical one calculated for the same system. Just to end with my presentation, I hope I have been able to show you how it's interesting to perform this type of experiment. You might get now excited as I am when I do this kind of experiment. The methods are very highly versatile, so we can perform the same experiment depending on the condition needed in laboratory scale and at the synchrotron if we need more fancy instrumentation or high resolution and so on, or even combined experiments. And with this experiment, it's possible to structurally characterize soft-XAS interaction, determine the binding site, and so on, and applying ab initio structure solution on the diffraction data to recover all the information about the adsorbate phase, the structure of the MOF during the process, and so on. So moreover, moving to more complex experiment, complementary in situ or operando experimental techniques are valuable tools to give complete information, not only on the average structure of the MOF, but also on the local environment when information of the local structure is needed to describe the system. I have to give an advertisement. So many students know that I am one of the directors of this wonderful school. The other two are Professor Jorge Navarro from the University of Granada and Professor Simona Galli from the University of Insubria and Como. And it's my pleasure to announce that we will organize in present the 3rd edition of the school in this beautiful villa whose name is Villa del Grumello. So there are students, I have seen that they have participated to the last schools in 2021 and 2019, and surely they are happy to tell that the place is nice, teachers are awesome, and so you are welcome when the application will be open to join us. And then I really need to thank my group. It's a small group. One guy is actually is visiting, but he's from a Jorge Gascon group. But so I have to thank Marco Vandone and Stefani Terruzzi for the work that I have presented today, and all my collaborators, because this is a work that needs a lot of expertise, and without them I could not perform it. So, and thank you very much for your kind of attention.
Thank you, Valentina, for this great talk, a great overview about the broad variety of techniques and materials. And I'm sure there will be a question. Yes, please.
Vitaly Sushkevich, Polshare Institute, Switzerland. Thank you for the lecture. I wonder whether you tried X-ray emission spectroscopy or valence to core spectroscopy to access the spin states of your iron VDC MOF.
So on the iron 2+ system, no. We have performed this experiment on iron mill 100 for other reasons. And maybe next beam time, we are in process of deciding.
So you do see the difference.
So, you know, our goal now is to show how powerful is this technique. So I think for the moment we will stop on this experiment and then see if we can perform another experiment, maybe also with the hard X-rays and combination with X-ray diffraction. It's known that through diffraction, peaks moves, so the unit cell shrinks when there is the spins transition. So a combination of the experiments, yes, would be interesting.
Thank you.
So thank you very much. In very interest of time, we have to move ahead.